Okay, so I was discussing the Yamabe problem on, say, singular manifolds. And so we have a solution of the Yamabe problem when, so weak formulation. So U solves the Yamabe problem. So LGU equal to R bar U to the n plus 2 over n minus 2, if and only if U is a critical point of this Yamabe energy. Okay, so this is what we saw in the past lectures. In dimension 4, let me also recall the counterexample by Vyaklowski. So from 2010. So he proved that there exists a 4-dimensional manifold, say, or there exists M4 with a metric G, singular. So with the one conical point, with the conical section or link. So here, the space X is S3 mod Z2. Okay, so this is a conical section. So on a manifold like this, so there is a singular manifold with one conical point such that the Yamabe equation has no solutions. Okay, so this is the one of the pathological examples we saw yesterday. Okay, so having in mind this result, I would like to state this theorem. So theorem B. So yesterday I stated one theorem in which for conical points with Einstein type section, we were obtaining existence of solutions for generic metrics. So theorem B is the following. So this is joint work with Mattia Freguglia. There's a paper on the archive as a preprint. And Francesco Malizia. So a paper from last year. So we are still in dimension 4. So that M4G be compact. With finitely many conical points with conical sections equal to S3 mod Z2 with a random metric. Okay, so let me call the conical points P1, Pj. So we assume that we have the same stringular structure as in Jaklowski's example. But the statement is that if we have at least two such points, so if j is greater than 2, then so the Yamabe problem is solvable. Okay, so Jaklowski's example has one conical point with this section, and it shows that for this example there is no existence. Okay, we show that if there are at least two conical points of this type, then the Yamabe equation has a solution. So let me compare to the two-dimensional case. So Jaklowski's example is like a teardrop. And for such a surface, there's no metric. So there's no metric with Gaussian curvature constant. On the other hand, you have the American football or lemon. Okay. And in this case, when you have at least, say, or two conical points, then there exists G with. So this is the American football. There exists a metric with Kg equal to constant. Okay, so in a sense, we have some sort of analog of this example. So let me just say a few words about the proof of this result. Okay, so it turns out that at these conical points, so suppose that we have two conical points of this type. Let me call them P1 and P2. Okay, so then at the conical points, the Yamabe constant at Pi is equal to the Yamabe constant of S4 times 1 over square root of 2. While the Yamabe constant at the regular points, so this is Y S4 GS4, if P is regular. Okay, so therefore, if you concentrate mass near the conical points, then the energy of bubbling is lower. Okay, so you might imagine QG to have a sort of double well potential. Okay, so near P1, near P2. It's like having two sort of minima. Okay, so they're not minima, but almost like minima. So what you can do here is to use a min-max theory. So we take a highly concentrated bubble say, U1 lambda, U2 lambda, okay? And we consider curves, so fix lambda large, and consider paths of this type. So paths joining U1 lambda and U2 lambda. Okay, so the problem with the min-max theory, so when you try to look for saddle points, so min-max sequences can develop multiple bubbles and something peculiar of this four-dimensional case. So in our example, or in our case, so for D, it turns out that the energy of two singular bubbles is equal to the energy of one regular bubble. Okay, and therefore, when you do a min-max scheme, you should try to avoid the formation of such bubbles. So we're able to construct a path whose maximal energy is below y S4 GS4. Okay, and therefore, so min-max solutions cannot blow up. Okay, I don't have time to explain the details, but somehow so when you minimize, you try to go below the quantization value for formation of one bubble for the classical Yamabe problem. In this case, you need to beat formation of possible multiple bubblings. And so we prove that there is a min-max path which cannot develop bubbling. So I list some open problems for the singular case. So we only did conical points, but it would be nice to understand say more general singularities. Like, for example, wedges. Okay, so there's no result about construction of solutions when the manifold has a wedge type singularity. Or I can mention the problem of prescribing conformally non-constant curvatures. Okay, so we studied the Yamabe problem, so constant scalar curvature, but you could prescribe any given function on the manifold. So try to prescribe the scalar curvature as this given function conformally. And for the singular problem, so there is a lot of literature on this problem. In the classical case, you can refer to my book, for example, where I collected some results in the literature. For the singular case, the only result I'm aware of is by Zhu and Vyaklowski. So this is from 3 years ago, 2023. And it's only valid in special cases in 4 dimensions. So for non-constant curvatures, the problem is almost entirely open. So I just know one single paper. Is there any question? Because now I would like to switch to a different topic.
So in your min-max construction, the min-max level is between the two levels, right? For the singular and the non-singular case, and that's how you get compactness.
And sorry, what is the question?
So the min-max level that you construct for the existence, so it is between the singular and the non-singular case, right?
Exactly. So
you get
the
compactness.
level, yeah, the energy level. So this is I call it y4, the Yamabe constant of the sphere in dimension 4. It's a y4 over the square root of 2, and here there is a y4. So essentially, we have 2 minima at this level here, and we construct a path which is below this other energy. Okay, so in this case, the enemy is that there might be formation. So you can prove that because the min-max value is strictly higher, so you need to you show that you go strictly higher than there's a gap between y4 over square root of 2 and some delta, so you go above. So the min-max sequence cannot form just one singular bubble, but it might form either 2 singular bubbles or 1 regular bubble. But we prove, so this is a hard analysis, that there is a path whose maximal energy is below y4. So there cannot be, you rule out all possible blow-up scenarios.
Thank you.
Yeah, that's exactly the point. Okay, so let me now consider the case of the so-called CR and pseudo-Hermitian manifolds. Okay, I presume that people are not so familiar with the subject, so I'll spend some time on preliminaries. And I will discuss the 3-dimensional case. Okay, so the setting is the following. So we have a 3-dimensional manifold, say compact, with a non-integrable two-dimensional distribution. Okay, so for any point P, there is a two. So we are sitting in a 3-dimensional manifold, and for any point P, there is a two-dimensional subspace, so Xi, so this is two-dimensional. It's a subspace of the tangent space of the manifolds at P. Okay. And we assume it's non-integrable in the sense that commutators, in the sense of Frobenius, okay? So commutators of vector fields that are tangent to the distribution can go outside of the distribution. I don't dare drawing a picture, but I can show you one picture. Okay, do you see it? Okay, it's something like this. So there are these two-dimensional planes that depend, and the orientation depends on the point. Okay, and when you move around, they kind of rotate. Okay, so the non-integrability means that these are not the tangent planes of a two-dimensional surface. Okay, if you move along a surface, then tangent planes go in some, I mean, they move with a point in a certain way. Okay, but here I'm assuming that when you move around, they rotate like this. So I hope it's kind of clear from the picture, and I will give examples. Okay, then on each plane we have, so on each XCP, so which is this two-dimensional plane, we have a CR structure. CR stands for Cauchy-Riemann. It's like a rotation. So J, think of a rotation of, say, 90 degrees, such that J squared is equal to minus the identity. Okay, so this is our Xc. So this is XCP, and J goes like this. Okay, so once we have a rotation, we can determine, so I use a complex notation. So complexifying the tangent space there exists some vector field or some tangent vector. Okay, so this is a Z1 tangent. So it belongs to the complexified Xi. In fact, so it belongs to Xi complexified, such that J of Z1 is equal to I Z1. Okay. So this would be in C, for example. Okay. So this would be dx minus I dy. Okay, and denote by Z1 bar the complex conjugate. Okay, now J is real, is a real operator. So J of Z1 bar is equal to minus I Z1 bar. And then I need a contact form is a one format theta annihilating the contact plane. Okay, so it goes like this. So generically, the kernel of a one forma is a subspace of codimension 1. Okay, so here we have a two-dimensional subspace of the tangent space, which is three-dimensional. Okay, so it's consistent. Okay, so non-integrability of Xi implies that, in fact, theta wedge d theta is non-zero. So this is a tree form on M. So we can use theta wedge d theta as a volume form. Okay, and if we have such things, so the triple M J theta is called a pseudo-Hermitian manifold. Okay, so why do people study such things? Okay, so let me mention a couple of examples. So the prototype example of such manifolds is the Heisenberg group, which you might have heard of. So this is like denoted by H1, and it's like the flat model. So it is just R3 with this group law. So xyt dot, so it's the sum of two vectors in R3. So this is defined as x plus x prime, y plus y prime. And for the third component, you take t plus t prime plus x y prime minus x prime y. And you can take, so what is the contact distribution in this case? So Xi is the span of these two vector fields. So of x defined as dx plus y dt, and y, which is defined as dy minus x dt. What is J? So J is such that Z1 So J is determined by the eigenvector corresponding to the eigenvalue I. So if I tell you what the eigenvector is, I tell you what J is. So Z1 is X plus EY. And in this case, the contact form of the Heisenberg group is dt plus x dy minus y dx. Okay, so this is the prototype example of a pseudo-Hermitian manifold. Now, now comes the real motivation for the study of such manifolds. So there is an algebra class of manifolds which comes from actually complex spaces. So boundaries of domains in C2. Okay, so we take a set omega in C2 to be, say, smooth and bounded, say open, smooth, and bounded. Okay, now we know, okay, that the boundary of omega is three-dimensional. Okay, because omega is a domain in C2, which is four-dimensional, so the boundary is three-dimensional. So we know what the tangent space is. What is Xi? Okay, so I need to identify Xi in the tangent space of the boundary. Okay, so I choose Xi to be the subspace of T delta omega, which is invariant by the action of the rotation in C2. Okay, so you just take the complex rotation in C2, and then inside the three-dimensional tangent space, you choose the two-dimensional subspace, which is invariant by J C2. Okay, so we choose the naturally J, so from C to itself, to be simply the restriction of the complex rotation in C2 to Xi. Okay, so that's the setting. And so Heisenberg was kind of the flat model, so with zero curvature. And there is a counterpart of the Riemannian sphere. So if we take as a domain the unit ball, okay, so if we take the boundary of omega to be S3, okay, so this is contained, I use the ambient complex coordinates, so it's contained in C2, which I describe as the elements of the type Z1, Z2. Okay, in this case, Z1 for S3 is Z2 bar dZ1 minus Z1 bar dZ2. So this is restricted to the sphere S3. And in this case, you can choose theta 0, so the contact form to be I over 2, and then sum for j running from 1 to 2 of zj dzj bar minus zj bar dzj. Okay, in fact, one of the purpose to study this pseudo-Hermitian geometry is to understand when two domains of C2, say simply connected, for example, are biholomorphic to each other. Okay, so pseudo-Hermitian geometry, it's written in this way. It's useful to understand by holomorphy. Okay, in C, so in one complex dimension, every simply connected domain is biholomorphic to the unit disk. That's a Riemann mapping theorem. Okay, but it's not true in general in higher complex dimensions. Okay, and okay, to understand this geometry, it helps to understand when two domains are biholomorphic one to the other. Okay, so because of this geometry, there is a little difference between the homogeneity and the topological dimension. So let me discuss homogeneous dimension and dilations. In H1. The point is that somehow the idea is that Xi, so the contact distribution, generates a distorted metric. Okay, so in which sense, okay, now suppose we are in H1, in the Heisenberg group, which is just R3, okay, and suppose, so in fact, at the origin, Xi of 0 is perfectly horizontal. And when you move around, then it becomes, say, more vertical. Okay, so when you move along the x-axis, this contact distribution is rotating. Okay, maybe I draw it very flat. It's a terrible picture, but yeah. So the angle is changing when you move along the x-axis. Okay. How do you determine the distance between 2 points in a smooth manifold? Okay, so you choose 2 points, you join them by curves. You can compute the velocity of a curve. And then the distance between 2 given points will coincide with the shortest length of a curve joining these 2 points. Okay, so the distance between 2 points P and Q is the inf of the length of, let me call gamma PQ, between all curves. Okay, so these are curves. Okay, but now we have a rule. So a rule in H1. So we require So we require that the velocity of the curves always belong to the contact distribution. So as a consequence, if we take P to be the origin and Q to be a point on the z-axis, okay, going up is forbidden. Okay, because the contact distribution at the origin is horizontal. And therefore, any such curve joining the origin and the point Q, which is on the vertical, must have velocity, horizontal velocity at the point P. Okay, so a curve joining the 2 points must spiral. Okay, so this will be the optimal gamma PQ optimal. It has to go like this. Okay, so that's the rule. And therefore, the distance becomes much larger in this way. Okay, it turns out that, so in this way, so with this constraint, the distance is distorted. So the distance in H1 between 0, 0 and the point with coordinates zt, okay, so z is xy, is more or less like this. So like rho of zt defined as z to the 4 plus t squared to the 1/4. Okay, so in a sense, the variable t counts twice. Okay, so the homogeneity of the t variable is twice as the homogeneity of, sorry, this is z to the 4 plus t squared. So the scaling in z and t is different because of this reason. Okay. So typically the distance between a point 0 and a point t, so the distance, so this is t, this is 0, the distance is of order square root of t if you are on the vertical axis. If you are horizontal, then it's just like the Euclidean distance. If you are vertical, it scales like the square root of t. And in this ambient, the natural dilations are the following. So the natural dilations are the following. So delta lambda of zt is lambda z lambda squared t. Okay, so it turns out that the homogeneity of H1 is 4. And if you compute, for example, the Hausdorff, in the sense of the Hausdorff dimension also. Hausdorff dimension, but computed with respect to the distance in Heisenberg. Okay, for Hausdorff dimension, you need to cover a set with metric balls, but here the metric is distorted. Okay, so the homogeneity is 4, while the topological dimension is 3. Is there any question? Okay, so on such manifolds, there is a notion of scalar curvature, which is called the Webster curvature. It was introduced in 1983 by Stephen Webster. Okay. The point is that it behaves conformally like RG. Okay, so in the Riemannian case, what you do is to rescale the metric. Okay, conformally. In the Riemannian case. In the pseudo-Hermitian case, what you can do is to rescale the contact form. So theta tilde, you can take a theta tilde, which is a multiple of theta. It's still a contact form, okay? Because the condition on the contact form was to kill the contact plane, okay? And theta tilde will do the same, okay? So the kernel of theta tilde will be still like C, okay? So that's okay. So this Webster curvature is a scalar quantity, okay? It's a function such that if theta tilde is equal to u squared theta, then the transformation law is the following. So minus, there is 4. This is sub-Laplacian of u. I will tell you in a moment what it is. Plus w theta u is equal to w theta tilde u cube. So the transformation law of the scalar curvature in the Riemannian case was by the conformal Laplacian. Okay, we had the Laplace operator plus the scalar curvature. This operator here is the sub-Laplacian. In a sense, it's the Laplacian only in the contact plane. Okay, so you take 2 derivatives, but only along this contact plane. So we're in 3 dimensions. So instead of taking all the 3-dimensional, all the 3 second derivatives, you only take the second derivatives in the directions of the contact plane, only in 2 directions. Okay. And somehow the fact that Xi is non-integrable implies that the operator delta B is so-called subelliptic. So subelliptic means that it gives you some regularity. So if so, this condition means that if delta B of phi is equal to f, which is a C-infinity function, okay, then the solution phi is in C-infinity. Okay, so because of the non-integrability, you gain regularity. Okay, so this is not true, of course, if the distribution is integral, okay, because if the distribution is everywhere, say, horizontal, okay, maybe then you control the horizontal derivatives of a function, but then vertically it might oscillate like crazy, okay? And, but due to the non-integrability of the distribution, somehow you're able to gain elliptic regularity. Is there any question? Okay. All right. So let me pose the CR Yamabe problem. Or maybe if I want to give a reference, for example, you can look at the paper by, sorry, a book by Dragomir and Tomassini. So CR Yamabe problem, we want to do the same. So we want to prescribe a constant Webster curvature. Okay, so we need to solve, this is the counterpart of the Yamabe equation, minus 4 delta B u plus W theta u equal to W bar u cube. Okay, and we want positive solutions. And this is an operator which I can call LB. Now notice this exponent, so 3. So this is like the Sobolev exponent in 4 dimensions. Okay, so 3 is equal to 4 plus 2 over 4 minus 2. It's like the exponent that you have in the Yamabe equation, but in 1 more dimension. And the reason is that the homogeneous dimension of the 3-dimensional Heisenberg space or pseudo-Hermitian manifolds is actually, the homogeneous dimension is 4. So the natural exponent here is 3, which is like the 4-dimensional Riemannian exponent. Okay, so how do you attack this problem? Exactly as before. So solutions are critical points of this quotient q theta of u, which is defined as exactly as before. So we have in general dimension some constant c tilde nabla subgradient squared plus w theta u squared, and then divided by the L4 norm of u squared. Okay, this is the so-called subgradient, which is just nabla of the function, but restricted to the contact distribution. Okay, exactly as before. And we can call y mj theta the inf of q theta of u. So let me copy these formulas. You can just repeat the same reasoning as for the Yamabe problem. Okay. So this is called the CR Yamabe constant. So we can actually repeat the reasoning exactly as before. So let me do a parallel. So this is MNG Riemannian. And this is M. Let me state it for general dimension. You can do the same, so you can define the same CR structure and contact form also on every odd dimensional manifold. So this is a pseudo-Hermitian manifold. Okay, so we saw that the manifold is locally conformally flat if and only if the Weil tensor of the metric is identically equal to 0. And here there is a notion of locally spherical. So it's like you are conformal to the Heisenberg group in general dimension, Hn, if and only if there is some tensor, so C, J, theta, identically equal to 0. So there's a tensor called the Chern tensor. So we don't need to know the expression of this tensor. So there is a tensor. If this vanishes, then the manifold is conformal to Heisenberg. Okay, in the Riemannian case, we have the estimate of Aubin. So Aubin's estimate so this was working in dimension n greater or equal to 6 if the Weil tensor was not identically 0. In the CR case, so in the pseudo-Hermitian case, we have work by Jason and Lee. So from 89. So there's a similar inequality, okay, as for Aubin. If the number n is greater or equal to 2, so the topological dimension is at least 5, which means the homogeneous dimension is at least 6, exactly as for the Riemannian case, okay? If the Chern tensor is not identically equal to 0. And they prove that y m j theta is strictly less than the y of the sphere with the contact standard CR structure and contact form, okay, implying that the Webster equation is solvable. Exactly as before. And then if we continue, so if we are in, say, if n is less or equal to 5, okay, or WG identically equal to 0, we have Schoen's estimate. Okay, and in this case, you ask, is there a positive mass theorem? Because Schoen used to prove the inequality on the Yamabe constant. He used the positive mass theorem by Schoen and Yau. So what about the pseudo-Hermitian case? Okay, so let me discuss now the mass in the CR in the pseudo-Hermitian case. Okay, so on the mass, on pseudo-Hermitian manifolds. So we saw that the mass, so the relevant term in the expansion of the Yamabe energy was the constant term in the expansion of the Green's function. Okay, so in this case, we look for the Green's function of the operator LB, which I call the conformal sublaplacian, so which is -4 delta B plus W theta. Okay, and how does it's like the Green's function in 4 dimensions, Riemannian. Okay, and let me recall the homogeneous distance, this one. So this is like the distance on the 3-dimensional manifold. So let me copy it here. So you can prove that in suitable coordinates, if you consider LB of GP, so P is a point of the manifold, and if you use coordinates ZT, so coordinates near P, so Z is complex, so Z and T form a set of 3 coordinates. You consider the Green's function for the sublaplacian, so which solves this. So you can show that this function GP expands as 1 over rho squared. So this is just like the distance squared. So it will be as in the Riemannian case, but in 4 dimensions. Okay, plus some constant A plus a big O of rho. Okay, and in the Riemannian case, Shen and Yao proved that the constant A is actually positive. So we want to understand whether we possibly have a sign on this constant A. Okay, so this would be the counterpart of the positive mass theorem. Okay, so it turns out that this is not always true. Okay, so there's a difference with respect to the Riemannian case. And there is a condition which still can guarantee positivity of the mass. So I need to give a definition. So a relevant concept for a manifold, so M3 J theta, so is said to be embeddable if there exists a map phi from M to some Cn, so to some complex space of some dimension, such that the push forward of the Z1 belongs to the complexified tangent space of the image of M, intersection with the span of dz1 dzn. Okay, so basically you want to find an embedding of the structure that preserves the contact distribution. Okay, and there is a theorem so this is due to Boutet de Monvel. in 74, saying that if you have a manifold of dimension 2n plus 1, j theta, so is compact, and little n is greater or equal to 2, so if the dimension, real dimension, is at least 5, then it is embeddable. Okay, so this is true if the real dimension is at least 5. Okay, now the bad news is that if n is equal to 1, then in fact most CR manifolds or pseudo-Hermitian manifolds are not embeddable. Okay, and there's an example. So due to Burns and Epstein from 1990. So a generic perturbation of course, the round sphere is embeddable. So because the sphere embeds in situ, so that was one of the main examples, okay? But if you perturb the structure, then it's no more embeddable. So a generic perturbation of the standard structure is not embeddable. Okay, and a theorem that we proved anyway. So this is due, so I stated as a theorem C, is due to Cheng, myself, and Paul Yang. So from 2017, is that if M3J is compact, embeddable, with first eigenvalue of the sublaplacian, conformal sublaplacian positive, then A is actually positive. And as a corollary, so from the positivity of that quantity, we can just reason exactly as in Schoen's work. So as a corollary, we have that if M3 J theta is as above, then Y of mj theta is strictly less than y s3 j s3 theta s3, and the Webster-Yamabe problem is solvable. So I will need to mention some work previous to ours by Gamara and co-authors, in which they did actually find solutions of the Webster-Yamabe problem of non-minimal type. Somehow following the strategy of Barry and Coron. So they use so from the end of the 80s, say around 89. So they used very strong topological methods to find the solutions of a min-max type. So with the positive mass theorem, we proved that under this condition, so if the manifold is embeddable, then actually the infimum of the sub-Riemannian Yamabe energy is attained. And tomorrow we will see that, in fact, this embeddability assumption is in fact crucial, because otherwise we have actually counterexamples. Okay, so I would like to stop here. Is there any question?
So you take the same test function, in the case of the Yamabe, you take the Green's function modified
Exactly,
test
yes.
function.
So that part essentially follows because we grew exactly so there are these bubble type of functions that were classified by Gerson and Lee.
Okay.
And we glue it to a suitable multiple of the Green's function of the sub-Laplacian. So the setting is exactly the same. Somehow the difficult part there was to prove the positivity of the mass. And for that, we needed crucially this embeddability, the embeddability condition.
Okay.
So we will see tomorrow that otherwise we have counterexamples.
Okay. Thank you.
Yeah, I didn't repeat the details of those because they are essentially identical.
Any other question? Any questions online? Okay, though no other questions, so let's thank the speaker.